Record. Yes, I'm start recording. Thank you. So there's something in the industry. It depends on how many of you would like to end up with software or hardware, right? There is a job. It's called verification engineer. So what is verification engineer? There's design engineer. There's verification engineer. Design engineer, normally you can be analog designer or digital designer. Analog designer, you're gonna work with PSPICE and PCB boards and all of this analog operational amplifier and all of this thing. Digital engineer, you're gonna be exactly like what we're gonna do now. We're gonna build the circuit based on the knowledge we learned from the 2300, which is the 204 for the people who got the 204. And then they're gonna apply all the syntax they're gonna learn on the synthesized code, and then they will deploy it on the chip. Then what will happen? Your code will be taken by Vivado in Xilinx or Quartus for Intel, or taken by Libro for Microsemi, or taken by Diamond by Lattice Semiconductors FPGA to be deployed on the chip. Okay? Or the same code, if it's generic, can be taken by Synopsys or Cadence, and people will deploy it on ASIC. Then it will be like a chip. Like, can somebody give me an example of ASIC chip? What is an ASIC chip you have in your life?
Sorry, Professor, can you repeat the question line?
Okay, again, so if you can hear me very well, I can put this microphone closer to me. So anyway, what I'm saying that there is two branches. Let me actually write it in front of you guys. That's better. 1 second. Let's go here, right? The branch of the job. We're talking about job market here, right? You can be a designer, or you can work in a verification. There's a verification engineer, designer engineer, or design engineer. Okay, so the designer can be analog or can be a digital design. Analog, op-amp, all of the circuits, we are using in the analog format. And I believe there is a course in the department actually dealing with analog info. Okay. Then digital, this is what we are learning. So in the digital, we learn the 2300 or the 204 if you guys coming from the quarter system, which is the digital logic design, right? Then they taught you in the lab all of this routing sense and wiring from the IC pin to IC pin and all these things. Do you remember? Now we are elevating a little bit, and instead of doing this wiring by our hand, we are using the hardware description language, VERILOG, as an example. So, but we are targeting what? Somebody tell me. We are targeting what? We are targeting two different ways. What is two different ways? We are targeting FPGA, or we are targeting something called ASIC. Sounds good? So the language VERILOG you are writing is targeting FPGA or the ASIC. Okay? Let's move a little bit. So FPGA, there is a multiple vendors. What is this vendors? Xilinx. There's another vendor, which is Intel, Altera. There's another vendor, which is Microsemi, which is now it's a part of Microchip. There's another one is called Lattice Semiconductor. Okay, all of those are vendors for FPGA. Sounds good? What we are learning in this course, it's not important that you can move to any of other vendors. It's not that really hard. So we are learning that we are gonna deploy the VERILOG in FPGA using Xilinx tool. And what is Xilinx tool we are gonna use? It's called Vivado. Early version of Vivado was called ISE. Are there any chips can be programmed using ISE? Of course. It's still in the archive. You can find it in their website, but it's up to 14.3, something like that. Okay, in 2014, basically. Vivado, what we're gonna do? We're gonna use Nexus 4 DDR, right? Or Nexus A7. Nexus or Nexus A7. Okay. Same Verilog code with a little bit tiny tweaks can be fitting into the Altera. But what program people use for programming Altera? I'm giving you all of this because this is very important for future, you know, Quartus. So Altera using Quartus. Sounds good? And then microchip. I have here a microchip in my other computer. Is using what? Libro. There is another vendor or company which is called Lattice. It's used for defense contractors. So basically, this one, the user program is called Diamond. So far, so good. This is the FPGA. But also, you can write a Verilog for this pass, which is ASIC. How are you going to program ASIC? That's not really hard. ASIC, you can program using two popular vendors, which is what? Synopsys or Cadence, using different technology. My question was, what is ASIC? What is the example in our life is ASIC? If you guys are following technology, what is the most popular thing that you have in your life which is made by ASIC? I can tell you, Intel chip, cell phone chips, yes, i9 in your computer, i7, all the motherboard are ASIC, right? My iWatch has ASIC. The microphone has ASIC. The camera I'm actually recording now, it has ASIC. There's a couple of cameras, and I have one in my office. It has FPGA chip, like Pexi. It's ASIC. Here, it's a sensor ASIC here. You know Pexi? So all of those guys are made by ASIC. Sounds good? I'm just trying to give you general rules. So now we understand Verilog is very important. Why? So why? Because, you know, ASIC or FPGA or whatever, all of these guys are programmed using what? Verilog or VHDL or what? System Verilog. So maybe I can add extra page here. So we have programming language is called HDL. This HDL, it can be Verilog, or it can be VHDL, or it can be System Verilog. Okay, all of those guys can be targeting all of these guys into the system. You know, they are using the Verilog's VHDL system Verilog to do what? To program ASIC or to program FPGA. Okay, but while we are programming anything, we have to have two ways. Okay, what is this two ways? I'm a designer, right? So people will give me what? A specification, specs. I give you a specification. Then I take my specification to do what? Yes, ASIC is not a company. ASIC, it's a chip type. It's a customized chip. ASIC is a customized chip. It's not a company. So Intel building ASIC chips. Altera, FPGA itself is an ASIC chip, right? Because they made a chip. So the one who made the chip maker is, you know, they built ASIC, custom hardware. But then they build also the ASIC of the FPGA, but the FPGA is reconfigurable. FPGA is reconfigurable, okay? So normally what we do as a designer, we go and talk to the customer. So your customer is an application customer. Come and tell you that, you know, I want you to build me a specific function. Here is the input, here is the output. I want the speed to be like this. I want the area to be like this. I'm expecting this, how much power it will be consumed and all of these things, okay? So that's gonna be written in your what? Spec. Then you take your spec and do what? You start designing. See, design. Using what? All the synthesizable syntax in one of those languages. Sounds good? Then you will ask the verification team to do what? Verification team will be waiting to run a software under the package of the Vivado or Libro or Quartos. They call it model sim. Model sim. What model sim does is basically connecting wires to the block you already built as a designer, and it's checking whether all the specifications have been met or not. If it found an error, they call it a bug. Then you will go ahead as a designer, you make modification, and you turn it back to the test. They will test the verification, and all of this are code. I'm not even testing on a chip. And that's called formal verification. Because I'm testing code. I'm not testing something real. I'm not actually testing here. Okay? Then once I feel that I'm confident, I will start the synthesis process as I did in front of you last lecture. Then you deploy, and after you deploy, when you are playing with the board like this to try turn on and off switches and so on, that's called testing. So you take the verification you did and to test whether that the thing is already happened or not. So this is whatever we're gonna learn up to the end of this course with more precise direction. Do you guys have any questions so far?
Yeah, Professor, how do we download the Vivado software? Last time it was a little bit quick.
So Vivado software to be downloaded is not that really hard. So, you go to the website Vivado. Here, let me share with you the screen. 1 second. How can I stop screen sharing? Yeah, I can say yes. I want my Google.
Sorry, never mind. I found it.
Okay, Vivado Xinex download. All right, here. Do you want me to send you this link, guys?
Sure.
Yeah, it's in the chat. So, also, as an engineer, be careful. You have to be very good in searching. That means you have to go in Google and use it very well on picking up whatever you're looking for. Okay? So if you look here, you will find multiple software have been provided by Xilinx. So you have Vivado hardware developer, you have Vetis software for the AI modeling, you have Vetis embedded system for the what's called microblaze and soft-core processors on ARM. You have Linux for embedded systems on the board, like, for BringZ, like the one I showed you here, I have in the camera, this one. And you have a device models, and that's a different for Ultra Scale Plus and Vertex Scale Plus for the military applications. So if I go in a Vivado, which is basically our target, there is a multiple versions here in the left side of the screen, right? So you can pick the 21, that's 2021, which is a version 1 for the 2020. Take this one, you go down, it depends on what is the Windows or the Linux operating system you have. I'm a person like, honestly, Linux. Industry Linux. Not that many people use Windows for industry. There is a multiple stories about why. But, I'm not gonna go too much on it now until we will be in an advanced stage, then I will tell you why Linux better than Windows. But anyway, you will go here, see, there is Windows, there is one here for Linux, I believe, and then is, single all of this. So you download all of this, basically, all operating system. That's around 35.51 gigabytes. And it's gonna be what's called compressed. So you have to uncompress it, and then, you will find the icon and you just install it. Then I told you also how to find the license. If you write here, Student. Nice. Here. Okay. Even there is course material you can find, like this, for instance, you know. Giving you the sketch, the PCB board, information about the specific board, basis 3 and Nexus 4. Nexus 4 basically the one we have, right? And also you can find it in a video, you know. Here, how to download and install Vivado. You'll find any video, you know, on YouTube. You'll find, you know, that's perfectly fine. Okay. Anyway, back to the.
Professor, I had a quick question.
Sure.
Does everyone in one group need to purchase the Nexus board?
What happened?
Or is it okay if you just have one person?
I don't know how you guys gonna do it, but I think it's better for you, all of you, to work together every single board.
Oh, I see. Okay.
I mean, this is the best, because don't forget, you know, it's not about to get the grade. It's about after you will leave the university.
Okay.
Make sense?
Yeah.
Yeah. Anyway, so let me get back to my notes. 1 second. Now we're back to my tablet, okay? So let's go into the information. So the history part, before you start learning anything, you need to know the history, right? So what is the history behind the Verilog? Verilog introduced in 1984. Okay, so 1984, if you go and study what was the first time for Xilinx to announce a certain product for them, an FPGA product, it was in 1986. So that means, you know, Verilog came before the company starting their job, right? And have been introduced by a specific community, which is called Gateway Design Automation. Then people start making their own version of the language. Like, you know, Mohammed make a certain language syntax, you know, for instance, you know, Mario did another one, Chad did something else, you know, Khalid did something else, you know, and so on. Then people come and say, this is not good, because, you know, if I'm exchanging knowledge between Mohammed and Mario and Khalid and Chad, we will not be able at the end and testing, you know, we will not be able to actually to have something common, standard. Then IEEE came with the first standard for Verilog. That means, as IEEE, or big organization for electrical and computer engineer society, they came and say, you know, everybody has to follow the standard, so everybody will not have any problem. Like, you know, everybody believed that the minute is 60 seconds, something. That happened in 1995, and they call it OVI Verilog. Okay? Then they started every single couple of years to revise. What does it mean revise? Until, for instance, they found a bug in the syntax. They will just report it in a proper channel to IEEE. Then, for instance, you know, Xilinx found something else. Maybe there is Draper National Lab in MIT, the one who worked for the space application, found something else. Then, you know, the community and, you know, the big hit guys in the Verilog part of the standard, they will come and revise, and they have a new version. And the newest version was 2001, 2005, 2009, up to maybe 2012. And then they said, what about if we add object-oriented programming perspective to the Verilog? And in this case, they call it System Verilog. Okay, so this is the historical part of the Verilog. Then, what is the Verilog? Basically, you know, it's a stand for the standard hardware description used to describe a digital system. So why we call it yes?
Anything that has to be changed about that, it has to go through IEEE?
Of course. It's a standardized thing. So you have to go through a channel reporting whatever you found, and after a while they will sit together to check whether it's a serious problem or not. And they will just improve it or clear it up or so on. They have their own programming team, you know? So anyway, so the stand for hardware description. So why is it called hardware description? Because the following: when you were connecting by wire to wire between pin to pin on your breadboard, that was description. So you're describing the situation. Like you go into the living room and say that I have sofa or couch, and then I have 2 chairs, and then I have the TV. The distance between the TV and the chair is this amount of feet, while the distance between the chair and the other is this amount of inches. So while I'm saying this, that's called the description language, because I describe to you the living room. It's the same thing. You're describing to me the circuit. And as I mentioned to you, this language is 2 pieces. Piece of the directive syntax for the synthesis, or like, deploying, and they call this RTL. While the other is for simulation purposes, to check whether that you have been written in the RTL is correct or not. Everybody know, even in the civil engineer and all of the designers in the different, departments here in Cal Poly or, other universities, they know that if you have a system and you consider verification with design is a steps for building the system, design is 40% of the effort, while 60% on verification. Some other scientists and stats guys, they say, no, the design is 35% of the effort, while the 65% is for the for simulation and verification. Sounds good? So verification is very important. And let me tell you something, verification engineer, they get a hell of money. They get a lot of money. So there is an approach of the verification is called UVM. People who have a training on Coursera. How many of you heard about Coursera? Okay, yes. So Coursera is an open education community. You can take as many classes from them, and you can even pay like $20 or so, they give you a certificate. Big schools like Stanford, Harvard, MIT, University of Illinois, Urbana-Champaign, I came from there actually, and then others, they have the top ranked professors give lecture there and open for the rest of the world to use it and learn out of it. And they have set of the UVM verification training. I would recommend all of you to take it. If you finish your study or you have time, go take it. Because I heard in the Silicon Valley, the salary for UVM verification engineer start from $175,000, which is a big amount of money, honestly. Okay, so let's take some terminology. Any language, it has terminology. So a common words, we're gonna use it often. HDL, what does HDL mean? A text-based programming language. That means I'm gonna describe my whole entire circuit based on the text, and I'm gonna describe the distances and all of these things between them together using this HDL language. Then, while I'm designing using this language, the HDL, I have 3 different approaches. I have 3 different what? Approaches. One of the approach is called behavior modeling. One of the approaches is behavior modeling. What is behavior modeling from your point of view? Behavior modeling, it means that, oh, I know this block, when it takes the input, it's gonna produce this output. So you are describing the transfer function of the block. How many of you heard of take any control course? So, okay, anyway, so if you have a certain block and you have a bunch of input and bunch of outputs, right? If you describe it, if you describe the relation between the input and output in just a way really quite easy to me, you are describing the behavior of this block. That's called behavior modeling. Example for behavior modeling, whatever you are writing C, it's a behavior, you're describing the situation, right? Then there's another one, it's called structural modeling. What is structural modeling? You imagine that you have component, you have the decoder of the 7 segments, and you have the encoder, and you have this bunch of switches, and then you connect between all of them together, and that's called a structural model. Example, when I built the multiplexer in front of you last time, I use AND and OR and NOR and all of those guys to build the circuit. That's called a structure model. Then there's a third one, which is a kind between of the structure and behavior, which is called data flow modeling. So the data flow modeling is using the concurrent statements in the hardware description language. So it allows a digital system to design in terms of its function. So it's not really quite high abstraction as behavior, but it's a lower a little bit than the behavior, which is called functional. So I'm describing function, which is describing the behavior. You have a question? Khaled? Hello? Let's stop sharing. Here. This Zoom is really bad. Now, okay. So behavior, as I told you, look at the behavior, right? So in the behavior, I have a box, and this box, it has a bunch of input and output going into the box. And then it come and say, that, you know, if some signals happen, be sure that the output will be, do you see this, the window sign? Basically, this window sign is actually saying that, you know, the output will be equal 0 after 5 nanoseconds. So you are saying there's some response time will happen, which will lead us to get the output after 5 nanoseconds. So that's a behavior. Structure, as you can see, I bring blocks like Lego set, and I connect them to each others, and I will declare that, you know, the input going there and the output is coming out of them. Okay. Then we need to learn more about terminology. So in this course, you heard from me several times, something is called RTL, right? So RTL stands for what? Register Transfer Level. So what is RTL again? Register Transfer Level. It's a type of behavior modeling, which is ready for the synthesizing operation. What does synthesize operation mean? So it means that I translate whatever I wrote in the VERILOG using the software I have. And what is software we have? Vivado. So the Vivado will take whatever you describe in VERILOG and you will translate it into a circuit level. Circuit optimized and represented as a circuit. When you say represented as a circuit, it will be represented as what? Transistors. If we are using ASIC. But if we are using FPGA, units on the FPGA is lookup table, LUT, or FF, which is the flip-flop. Later on, you're gonna have a set of slides describing the relation inside the FPGA. But for now, you need to know what does synthesize mean, or synthesizable. RTL, synthesize, mean that, you know, I will take whatever written in VERILOG and I completely convert it into what? Circuit. So far what we learn what is HDL, what is the different modeling that I can actually approach using VERILOG, starting by behavior versus structure versus the data flow, right? Then example clearly about how every single model works. And then the rest of the terminology, which you're gonna hear it often in this course, which is the RTL, stands for the register transfer levels, and the synthesis of this, and that RTL synthesizing of this operation. So the synthesis is an operation made by the tool provided, and the tool in this course is Vivado. Here is the description. So the one in the left side is a piece of code written using VERILOG, which is inferred into describing a multiplexer. But then when I synthesize it or translate it, it will be a bunch of gates. And these gates will be optimized to build multiplexer, as you can see by the end of this Y block. See? So that's way easy for you than having yourself in the lab with a bunch of wires connected to the, from the left to the right to the top to the bottom. And then, you know, one of the wires will be missing. Then you have to unplug everything and put it again. How many of you have this problem before? While you are in the lab, you are running the 2300 experiment, and then for a reason or other that you found something is not working. So unfortunately, you have to completely remove everything and do it from scratch. Painful or not, it's really quite painful. Do you agree?
Totally.
I know, I agree. I was a student and I know it was really painful. But you will love this Verilog if you fully understand Verilog. You will be like, every day I said, I want to build something with Verilog. And actually, I love Verilog. Even, my PhD was using VHDL. VHDL is the Air Force language, basically. They call it the Air Force baby. Because, Air Force is pushing this language more than Verilog. Who is using Verilog and system Verilog? Industry, the civilian industry. Like, Intel, IBM, all of these guys around us using Verilog. I think maybe Jet Proportional Lab partially using also Verilog. Yes.
So Verilog is basically what is used more?
Yeah, Verilog is used everywhere. VHDL defense.
Also, so when we write the code on the FPGA, is it similar to how assembly and C work on?
No. I will come later for this. Verilog, or how the description language, is a parallel language. So debugging it is really quite hard compared to debugging sequential language like C. Assembly sequential language. Because you execute instructions to go back to another instruction, to back another instructions, right? In Verilog, you can find a bunch of them running in parallel, doing something different. And then you have to shift them.
I understand that. I know that. I'm just asking, like the code, when we write the code, is it like stored just the same way it is stored with the microchip, or does it always?
No. It's not a memory thing. It's a code will be converted into a bunch of binaries going on the chip to be mapped as an FPGA product. It's completely different. Okay. Anyway. Honestly, I really like defense projects, but anyway, so I like more VHDL, but Verilog also is not that bad, Anyway, typical RTL synthesis process, What is this process? So the process is the following, right? I write my code, I give it to the Verilog model, basically I wrote it. So I pick up my model, right? I will decide as Mario, for instance, and come and say, Professor Ali, give us the specification of a certain problem. So I think it's the best way for me to build this module, we call it module in the Verilog. We're gonna use maybe data flow modeling. Then he will start using the data flow modeling approach, and then he will close the green left one, which is called Verilog model. Then he will start pushing this code into the Vivado first step, which is called synthesize. Then synthesize, that means you're going to use the technology. If you remember in the beginning of the first lecture, I opened in front of you Vivado with multiple steps, one of them identifying the chip we're going to use on the project. So this is the technology library. Both of them will go into the synthesize compiler and bring something that's called netlist. This netlist, you have timing of the circuit coming from the 2300 knowledge, which is something that's called critical path. How many of you still remember critical path? Any of you heard about critical path? Just one person did like this. Anyway, yes, thank you. Now, no, he said no. Okay, so there is no problem, Anyway, so critical path is the longest delay between the input and the output. This is the longest delay. And that's called the critical path. I will just move forward a little bit, then I will go back to critical path and I'll show it to you. Even it's not a part of the course, but I will do it, okay? Anyway, now I will go into the place and route. It's another step going further down until I will get into the switches on and off on the FPGA, so the file will be generated as bit stream. While I'm doing this, I can actually run simulation to check that the compiler already did what? Translated every single step correct. Example, for instance, if I speak an alien language, and somebody else here in Cal Poly understand my alien language a little bit. Then I describe to him something in my dialect of this alien language. But he didn't understand the dialect, and he misunderstood the whatever I'm saying. So that means he's gonna translate to the people on campus completely wrong. You agree? Same thing. If you write a code in a bad way, in a bad fashion, the compiler might not understand you 100%, and it will bring a crap out. How are you gonna figure out that the compiler give you crap out? Simulation. Simulation will come and tell you, oh, did you really actually did you really mean that, you're gonna do this and this? Then, that means feedback, right? Then the feedback will come to me and say, no, I didn't mean that. Then I will try to find a different way to describe it to you until, you will come and say, did you really mean this? I said, oh, yes. And he will move forward. That's exactly the story. Okay? So if you look to the other side of the slide, simulation also has its pieces, right? You write a test bench. Then what? Test bench in the Verilog, you can actually feed data from text file based on a library. Everybody, I'm sure, heard about it. It's called text.io. How many of you heard about text.io? You have a certain library. It's called text.io in C. If you didn't hear about it, there is no problem. We're gonna learn a lot here. Okay. Anyway, so the text.io will be pushing data into the test bench. Test bench will take it and hand it into your module, and the module will be generating output. Then you will see the output and input in some weird toggling environment. It's called waveform. If we go more into the verification, we can do something that's called assertion. And this assertion is mean that instead of looking by your eyes to the waveform, you will make kind of rules. If the design while is running the test bench is failing one of them, the whole thing will be stopping and say, I stopped in this point because something wrong happened. So that's called what? Formal verification. Since we just have 15 weeks, I'm gonna do my best to cover everything, but as I told you, still there is a part on you need to learn from outside resources as well. Okay, anyway. Now, how can we model in general Verilog? Like, in C, you have to say main, and then this curly brackets, and then the parentheses, and then you put void, you put whatever, and you make return and so on. This is the hierarchy structure of the code itself. But for the code in Verilog is a little bit different. Why? Because first of all, inside the file, let's say the file will be named. The file will be named, pretty much you will name it with the name suitable to the module process. So let's say that you are describing multiplexer. So call it max.v or multiplexer.v. So the file extension in Verilog is .v. Make sense? Then you will go and say module and the name of the file again, and parentheses with semicolon. What inside this parentheses? You're gonna write the port declarations. Normally, any block in general in hardware, it has input and output, right? So those ports can be input, can be output, can be in, out. This is the only three possible things that you can see in hardware, right? Something input or output or in, out. Pretty much people use input outputs. Little bit use in, out. Make sense? Then you will follow by data type declarations. You declare the type of this in and out, and you will start describing the circuit functionality and put the timing specification into the account of the module, and you close the module by writing in module. While you are doing this, be careful. This is a case-sensitive language. That means if you name an input port or output port with a variable like x lowercase, then you want to call it in the functionality of the circuit, and by mistake you make it uppercase. Then the compiler will tell you wrong. because it's a case-sensitive language. If you want to make a comment, single comment, you can make the backslash twice, double backslash. If you want the multiple line comment is like C, backslash, star, and you put whatever you would like to comment, you close it with a star backslash. Timing generally will go into the simulation, and I'm gonna show it to you as well. Example of the port declaration. Example of the port declaration. So module, and then I call my circuit, it's called multi_ACC. What does it mean? Multiplication accumulation. So that means my file, it will be what? MULT_ACC.v. Sounds good? Then the parentheses, it's actually sorting all of the possible input-output ports I would like to work with. And then you make your input, the size of the input, and all of these things, and then you start writing. Sounds good? I'm gonna move a little bit further. Maybe it's not really clear, but it will be clear when I will open Vivado in front of you and I do different combination things. Now, type of the data. So for you, for instance, in C, you have the type of data: float, integer, whatever, right? Or long, short, integer, whatever, 16, 32, 64, and so on. There is different. There is a type of data. They call it net data type. And what is this type of data we have? We have wire, TRI, or trie, or supply. What is those? So wire, that means this is just a wire. It's not storing any data. It's just passing data from point to point. That's basically describing the same thing as when you have two ICs in the breadboard and you are connecting wire between the pin to pin. That means there is no resistance between of them. It's just a wire, right? Then try, how many of you heard about the tri-step buffer? The block is different, so I will tell you about the block. But anyway, do you hear what I said? So the try, how many of you heard about the tri-step buffer?
Heard of it, but I don't remember what it is.
It's 2300. So the tri-step buffer is a wire which has controller. The third wire is controlling whether the input will go to the output or not. It does act like a mux, but it's not a mux. It's called a buffer or tri-step buffer. Anyway, supply, it's a kind of logic. Do you want a logic constant? So in that case, you will store the constant under supply. Make sense? Then, how can you declare bus also? I would like to declare a bus. So the data type of the bus and the size of the bus, and then the name of the bus. Example, as you can see in example, wire, it is a wire. And how many wires of this called out? It's from 7 to 0. So most likely we write most significant and then column least significant. Okay? And then try enable, you can do whatever. I don't use this try things because actually it's cause a lot of issues. Then there is also different type of variables we can use, like registers. So you have wire, you have registers. Registers, if you are storing data. So for instance, sequential circuit. If you have anything with a clock, use register. You cannot go ahead and say, oh, I have a clock, but I'm checking the value in the wire. That doesn't make sense. You know what I mean? Because if there is a clock, that means there is a register. There is a flip-flop. You're going to store something. So in that case, you will use reg. Okay. Then also we have integer, we have real and real time, and all of these guys are basically simulation environment, not synthesized environment. If you want also to define the reg, that's not really hard. Basically, you can go ahead and do it, and you will say that reg 7 to 0 and out, as I mentioned to you. Then we have something is called model instantiation. So what I'm going to do, I'm going to stop on the model instantiation and open Vivado so we can cover whatever we talked about now. Then we will back to the instantiation. Sounds good? So because my computer is very slow, I will open momentarily. 1 second. Where is my Vivado? Vivado. Vivado. Takes some time, sorry for that. Anyway, maybe I can go through the instantiation also until the Vivado open. So an instantiation means that, imagine that you build a block, and this block, like, you have how many 7-segment display in the design? Let's say 2, right? And then you bought a component of the 7-segment display, right? You know that the decoder of the 7-segment display is the same as a mirror, right? Same thing. But you're gonna use it twice because you already have 2 different 7-segment display, right? Because you use the same thing twice, it has 2 different names. This process in hardware description language is called what? Instantiation. It's called what? Instantiation. That makes sense? So there is a process to instantiate. You can instantiate with delay. You can instantiate without delay. We can also have an example about instantiation soon. And I already give you here an example about instantiation you can find in this slide. So now Vivado is open. So I'm going to share with you Vivado. Share, yes. Can you see Vivado? Everybody can see Vivado?
Yeah.
Okay. So normally when Vivado open, you say create project. That's the first thing. Unless you have a project you would like to resume. So you say next. I'm gonna call the project with a name. What is the name we can call the project with? Let's say, I don't know, whatever, full adder. Right? Then next. It's gonna be stored in the ECE3300 course underscore 4, okay? Then we are targeting to deploy on the FPGA what RTL, so that's why we keep it here RTL. And click. And the number of the chip on the board, it's XC7A100 TCS, and then -1. I remember it, But I showed it to you before. You can get it from the back of the board, or you can find an internet. Where's the board? Somewhere in the 5th dimension. Anyway, next. You finish. Okay. Now we have design source. They have constraints. They have simulation source. Everybody can see the Vivado still? Can you see Vivado?
Yes.
So you see design source and constraint and simulation sources, right?
Yes.
Okay. So I'm standing now on design source, right? I'm gonna stop in the constraint and say add source. I just say add source, right? 3 different categories of add source I can do. I add constraint, or I add design, or I add simulation, right? Because I already defined the chip as a technology model, return it back to one of the slides. You already have a copy of my slides. So you will find that, I said model with VERILOG model and go in the synthesis, right? So here I will just say I would like to design, create my constraint. And my constraint here, create, I would say what is called Nexus for DDR. And it will be created in a second there, which is completely empty. So I'm gonna go back to the internet and just write Nexus for DDR. You cannot see it, so I have done this last time in front of you. So I will take a copy from the GitHub, the official GitHub of them, and take a copy and go here and copy it. So I have now all of the commented file. So by the way, I told you in the Verilog, the comment is basically double backslash, right? But the comments and the comment in the txdc file using the hash. Look, this is the comment. Like, I can write here comment and say, this is first try of using the xdc file. So when I do this, nothing will be what? Synthesized or actually taken care by the compiler. Anyway, now I need to do what? To design. So what I should design from your point of view? Let's design multiplexer again as an example. Just I repeat it now after what we have seen. So I will just go ahead and say add source and say design. No, I said full adder, right? Sorry, design full adder, I'm sorry. So design, and I say full adder, right? Then I say create, and I call this FA, because it's gonna be FA also. And then I say finish. And I can actually make it by any way I want. I can make it by the compiler or like this. I can write it in front of you, or I can just write it by my hand. I like my notation. So my notation said in the document, and somebody can even look at it now. Can you please, everybody, open the document in front of him? The one, I give it to him, what's called? The slides. Normally, when I write, I told you, you already have a module in the module, and then what is the name of the module.v? It's gonna be FA, right? Then if you remember in the parentheses, you're gonna put what? The input output ports. One of the way to do it, as I mentioned before, you can just write the name of the ports. So we have ports is what? We have A, we have B, we have CN, which is the carry in, and we have sum, and we have carry out. Vivado, the newest Vivado, consider A and B and C out are not declared. Why? Because the newest version of Verilog, you have to go inside the parentheses itself and define them. Okay? How? So A is what? Input. B is what? Input. Cn is what? Input. Sum is what? Output. Carry out is what? Out. So what I did, I declared the input and output inside in the parentheses. That's one of the changes have been made by what? By the revised version of Vivado, which is fine, okay? Now, you have to declare the output. You have to declare what? The output. Are you guys following me? Is there any question so far?
No question.
Huh? No question, okay. So A, B, Cn, and sum and carry out. Do you remember the data type we mentioned before? So the output, what is the type of the output will be? Either it can be register, it can be wire. So something you have to put it here. Look, I'm gonna make comment. You should know that the output has to be declared either as wire or rig to be sure everything is working fine. By default, the output is wire. So by default, the output is wire. But for my notation, put 1 million lines under this. By my notation, I want to be sure to is wire. Okay, so in that case, the course notation has to be followed as if you need the output to be wire, put it as wire. What does it mean? We will go here and do it. Sum is gonna be wire. And I said the output by default is wire, but I'm gonna write it. So I'm gonna here write. Did you see what happened? The color, it changed from the purple to red because you know this is the type of data. That makes sense? Then the carry out is also output. Is it gonna be wire or register? We don't have any clock here, right? So we're gonna make it what? Wire. So now we have what? We have both of them wire. Sounds good? Now, this is what full adder. Do you agree? Full adder is a combinational circuit. Do you agree? Since it's a combinational circuit, you have to think about whether that you're gonna build it using behavior model or a structure model or the data flow model. That makes sense? Let's go and do it. But before, I'm gonna remind you what is the critical path. So I'm gonna switch back to my tablet so I can share with you how we can build and refresh your knowledge about how to build a full adder. Don't worry about this. You can come and see and say, here, I'm gonna make my full adder specification, right? So I have a block. Is this 1-bit full adder or multiple bit full adder? It's 1-bit full adder. So here's 1-bit full adder. How many input outputs I have? I have A and B, and I have sum, and I have carry out, and this is my full adder. Right? Design rules 2300. Huh? So I'm gonna build it structurally. So I'm gonna build it what? Structurally. Hear it very well, structurally. So I need to have A, B, C, N, and sum and carry out. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. And here is my sum and carry out. Do you guys remember the 2300? So here is 0, here is 1, here is 1, here is 0, here is 1, here is 0. Somebody's in the waiting room. Zero, 0, and 0. All right. Here is no, I'm sorry. Here is 1. Here is 1. Here is 1. Here is 1. Here is 0. Here is 1. Here is 0. Here is 0. Here is 0. Right? Sounds good. Okay, now design process, if you guys remember. Design process, I need the sum to be written in the Boolean algebra, which is gonna be A XORed with B XORed with C. Then carry out is basically A ended with B, and A ended with C, and B ended with Cn. Circuit-wise, XOR A, B, Cn, here's the sum. Now I'm gonna change my color to be A with B together. Then another color, B with C together. Then different color, OR. Then A with A with Cn together. Then another OR gate, C out. You guys agree? Now, what is the critical path? Critical path is the slowest. Now you already have 3 players, A and B and Cn. They are in a race line, waiting for me to, use the whistle. They will run to win. So, what is their final destination is the output, right? Normal race, everybody's running, and the fastest is the winner. For us, the slowest is the winner. Why? Because if the fastest arrive, he will arrive with the wrong answer. The slowest will arrive with the right answer. Make sense? So we need to identify something is called critical path. So we need to know all the different passes between the input and output. So here is one pass. All right? Then here is another pass. Then here is another pass. So I have 3. And then there another one. And then there another one. And then here another one, and here also another one, and here also another one, and there's another one. So all of these are the passes between the input and output. Do you agree? In that case, we need to know what is the slowest. How are we gonna know the slowest? Somebody can tell me. Hello? You guys hear me?
Yes.
Yeah, so how I will know the slowest? There is a
whichever
information here. Huh?
Is it whichever one goes through the most gates?
Yes. So first of all, the missing information I'm looking for is what? Response time of every single gate. Right? So I can come and say that, response time of every single gate. It will be defined by what? Silicon. So normally they define it by NAND or NOR. By NAND or NOR. So if somebody in this circuit come and tell you, I'm using NAND technology, and every NAND gate is taking 1 nanosecond response time. What does it mean? It means NAND gate, it take the input and produce the output after 1 nanosecond. So in that case, we have to be tricky. Why? I will tell you. I don't know what exactly happened, but that's fine. Anyway, so so in that case, I need to know what is the AND gate using NAND. I need to know what is the OR gate using NAND. And I need to know the XOR gate using what? NAND. And from there, I will apply it here, and I will know the longest path. Do you agree? So let's do it. I'm just reminding you. It's just refreshing your knowledge. So AND gate is what? AND gate is C is equal A AND with B, right? But NAND gate X is basically Y Z complement, right? If I want to build inverter using NAND gate, what should I do? I will bring my NAND gate like this. If this X, that's gonna be X complement. That makes sense? So in that case, if this one in front of me is AB, but I'm using NAND gate to build AND, so in that case, you know, the AND it will be, 1 second. It will be NAND gate. Here is A, here is B. So the output is gonna be AB complemented. That means if I go ahead and put another NAND gate like this, so the output will be A, B, and it complement. This is basically equal what? Nothing. So I can literally remove those two guys, and what I used from the 2300, something is called De Morgan. Have you guys remember De Morgan?
Yeah.
Yeah.
Yep.
Exactly. So now I built the AND gate, and I set the response time for the AND gate how many? 1 nanosecond. Do you remember? So this is 1 nanosecond. This is 1 nanosecond. So officially, I can say 2 input AND gate using NAND. Scheiße. My phone like to talk to me all the time, you know. It seems that, you know, my phone is also attending. Anyway, so it's gonna be 2 nanosecond. Sounds good? So we figure out that
Is that for AND or NAND, the 1 nanosecond?
Mister, I use the NAND gate to help me to bring the AND gate.
Oh, okay, yeah, I got what you mean. So the AND gate is 2 nanosecond.
Yes, because I know the NAND gate is 1 nanosecond. So I can go here in this circuit, and I say here 2 nanosecond, 2 nanosecond, 2 nanosecond. Right? Now I need to remove the OR with something, right? So I return it back here and say add page. Scheiße. I said add page, I didn't say put the something. That's crazy. Anyway, OR gate. What is OR gate from your point of view? OR gate is Z is equal A OR with B, right? So in that case, I know
OR gate.
I know no a NAND gate. I'm gonna use NAND gate. Everything's NAND gate. Anyway, so gonna be here X be a complement. That's basically the NAND gate, right? So what I can do, I can break up this to be B complement or with A complement. So this is actually the equivalence of what? Of NAND gate. This is the NAND gate, right? So what I can do, I can be tricky. How I can be tricky? I can actually go here and remove A, and I make it A complement. Sorry, I make it like this. To be A complement plus B complement. No.
No, I think that's right.
No.
That will end up with the AND gate.
No, they're gonna make it end. Do you agree?
Yeah.
Yeah, it should be an and when you use the
Yeah. No. I'll do it. It's not really hard for me. It's a piece of cake. I want to build A plus B using this, right? So that's gonna be A complement, B complement, like this. All right.
Can we do that A complement plus B complement will become A complement times B complement.
No. What we can do like this. Wait. We can do like this. Right? De Morgan. If I add two of them, there is no problem, right? So I can go ahead and say that's gonna be A complement, B complement like this, right?
Yes.
And then, I remove this and I call it C, and I remove this and I call it E. So that basically is E, C complement. So this is thin NAND gate, right?
So for OR gate, on OR gate, we would use
So
3
OR gate will be like this. So here is the OR gate, right? Do you guys agree?
Yes.
Yes, super. So this is 1 nanosecond, this is 1 nanosecond, this is 1 nanosecond. So they are two identical actually passes, right? So this is actually 2 nano and this is 2 nano. So I can say that every OR gate, it will be replaced by 2 nanosecond as well, right? So here I can just say 2 nanosecond, 2 nanosecond. That's it, all right? Now we are coming into the funniest part, which is what? XOR, right? So in that case, we go and say XOR. What is the equation of the XOR? XOR is A, B, B, like this, all right? Do you guys agree? I know my OR is like this. This is my OR, right? Then there's two branches. One is for this, one for this, right? Huh? Everybody following me? Hello?
Yes, I'm following.
Super, thank you. So this is an OR, keep as an OR like this. Now, one branch is gonna be AB, which is N. So I know my N, right? I know my N, right? So my N is what? Somebody tell me. So it's gonna be like this. Another one is N also. Then when it has A like this and B like that, and when it has B like this and when it has A like that. Do you agree? Do you guys agree with me? So
Yes.
there is another trick we can apply. If you invert the invert, you didn't do anything, right? So pretty much I can come and say, those two guys are wire, those two guys are wire, right? So I can just move them and say it's gonna be like this, and then like that, and then like this, like that. No, one sec. Let me clear it, pum pum. Yeah. This is the B and this is the A, right? And then, I can get a different color and say this is going like this, and different color, and this going like that, right? Now we are looking for the longest pass. So the longest pass is gonna be 1, 2, 3, and I think also this also 1, 2, 3. So we have here 1 nanosecond, 1 nanosecond, 1 nanosecond. So we are talking about what? 3 nanoseconds. So every XOR you can replace with what? 3 nanoseconds. So you can just go back and put here 3 nanosecond, 3 nanosecond. So far, so good? So if you look at it, you will find that, the longest pass here, this is the pass which is 6 nanosecond. And there is another pass here going to be 2 plus 2 plus 2. They're going to be what, 6 nanosecond. And this one also going to be 2 plus 2 plus 2, going to be 6 nanosecond. And here we're going to be just 2 plus 2, 4. New is 2 plus 2, 4. So the longest is 6 nanosecond. Do you agree?
Yes.
Yes. So the longest circuit is basically the longest pass 6 nanosecond. So I have to operate my circuit in 6 nanosecond. Every 6 nanosecond, I will take my output. So now, is it the critical path is very clear to everybody? Yes, 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 yes. But I'm saying the longest one. Let's say that all of them are very shorter than 6, but one is 6 nanosecond. Then every circuit, the whole circuit has to be 6 nanosecond. Let's say that all of them 6 nanosecond and one is 2 nanosecond. All of them gonna be 6 nanosecond. Got my point? That's called critical path, longest one. Okay. Now we will back to Captain what's called Vivado, right? So Vivado here. Okay. So if you remember from the documentation I'm sharing with you, we said after you declare, we declare between the parentheses, and it's very clear, right? Now we're gonna make it a structure, for instance. Okay, so how a structure? So basically I said I have an XOR, right? So I say XOR of what? I'm XORing what of what? A and B, right? And I'm producing C, right? Do you agree? So maybe I have to turn it back a little bit to my tablet again, I'm sorry. Just to show you something to be aligned, because they're gonna really very important to you and the understanding the course. So have you noticed something? Look at the circuit we built, right? So the XOR we have here, right? It has A and B, and this XOR, the output of this, we're gonna name it with something. That's a wire, right? So the output of this, let's call it T1, right? Then T1 going with Cn to bring what? Sum. So pretty much I will need, as a structural engineer, to build structure modeling of the circuit to produce wires called T1. Do you guys agree? Then here in NAND gate, for instance, A and B getting the output here. So let's call this one S1. Then S2 here. Then S1 and S2 will bring S3, for instance. S3, this is S4. S3 and S4 will bring S carry out. So are you following my idea, right? So now I'm gonna do the same thing in front of you in the Blackboard. Sorry, in the, not Blackboard, Vivado, I'm sorry. So we go back to Vivado and say yes, and then we're back to Vivado here, and then we'll do the same thing. So we need to have a couple of the wires to describe the relation intermediately. So now we said, wire, and it's a single wire, so it doesn't need to be a bus, because if it's a bus, it's gonna be the most significant to the least significant, and you close the bus and you name the bus. But for us, no, it's a single wire, so you just make it one wire and you call it what? T1. Don't forget, this is a what? Case sensitive language. So I'm gonna use T1 as a lowercase all the time. Then I need another wire for the S1, S2, S3, and S4, right? So I need S1. And because of all of them single wire, I can just make them in one line. It's called wire. You know what I mean? So I call S2, S3, S4. Sounds good? Now, XOR, the output of it is T1, and the input of it is A and B. Then that T1 will go with what? Cn. So XOR, the output of this is gonna be sum, and T1 will gonna be with what? With B, with T1 with Cn, I'm sorry. Somebody message me or something? If anybody in a question, let me know. Where's the chat? So the critical path issue can be helped with the carry look ahead generator with an adder improve the critical path. Yes, yes, Mario. Because by the way, the full adder has two different designs, and we're gonna talk about this. One is called RCA, rebel carry adder, and the other one, which is called what? Carry look ahead adder. Okay. Anyway, back to the point. So the carry here, so you already got the sum out of this XORing, right? Now we need a bunch of AND, right? So we're gonna say AND. What we can do, we can just make also some comments helping us. This is the design part for the sum output. Now I'm gonna make this is the line part for the carry out output. So if you look to the thing that I was doing in front of you, so I have one AND. Of course, I'm expecting the output to be S1 and the input are A and B. Then I have another AND. It has the carry in, let's call it S2 for instance, and it has the carry in with B. Let's say it has another AND, which has also S3, and it has C in with A, right? Then we have an OR gate, right? Taking S1 with S2 to bring S3. So sorry, S4. S4, you're gonna bring S1 and S2 to bring S4. Then I have another OR gate, which is bringing the carry out with the S4 and what? S3. No, right?
Sorry, I couldn't quite hear you.
Hey, what are you talking to me? Siri is annoying. That's called carry out, mister. So did you notice what I did now, right? So what I did in front of you is a structured modeling, period. Sounds good? So as a person, as a question also for the exams, if I ask you and say design, so that means you have to do everything. You have to make a simulation. You have to check whether the whole design is working correct or not. And you point to me that, everything has been covered from the specification perspective. That makes sense? Now I need to test my circuit. So what I can do, I can go ahead and say that also at source and simulation environment. And in this case, I'm gonna call it what? FATB, which is a test bench perspective. And from there, here's the thing I need to tell you about the test bench. This bench doesn't have input-output ports. This bench doesn't have what? Input-output ports. This bench is empty in terms of the ports. So you just say, yes, it's empty. And from there, you open the parentheses here. This is my test bench. So while you are in the test bench, you have to be sure this is empty. There is no need to have input or output ports declared in this section. But you need to test something. Do you agree? What do you need to test? Somebody tell me. What we are doing now, we are testing what? We are testing the functionality of the full adder. Do you agree? So we're gonna do something is called what? We're gonna do something is called what? It's called instantiation. What we're gonna do? We're gonna do instantiation. So do you remember the instantiation I mentioned? So the instantiation, what is the name of the Verilog folder that we, Verilog module we made now? FA as an uppercase, do you agree? FA. Then, because you can instantiate it many times, you have to give it a name. You cannot instantiate it like this FA, because you can call it multiple times in a file, like a multiple subroutine. So in that case, I'm gonna call it was what? Let's call it unit 1. Then you open the input output ports area. If you remember the input output in order, you can make it. If you remember the input output in order, you can make it. Like you put them in order. But before, this is like a block, right? Like you bought the IC, but you know, how are you gonna test it? You have to connect it to this power supply and all of these things, right? So you have to also to connect. So this folder, or this full adder, I'm sorry, it has how many input and output from your point of view? Somebody tell me. It has 3 input and 2 outputs, right? So I'm gonna call here what? Wire A, TB, wire B, TB, wire CN, TB. So those are the possible 3 inputs we have, right? Now rig some TB. Those gonna be output. Rigs carry out TB. Why I call them TB? Because they're environment of the TB, this bench, right? So if I know the order, if I know the order is basically A and B and C and sum and carry out, I can just put it like this. I can say, A, TB, B, TB, C, N, TB, sum, TB, carry out, TB. And I close. So what I did, I connected those to the full adder. But normal case, like, while I was working for Atmel, we are building processors. So building processors like millions of input output ports. So are you gonna remember all of them by heart? Remember their name by heart? Of course not. So in that case, you have to go ahead and just, if you can comment this out like this, and say it's gonna be FA unit 1. And I like it to be like this. Then, do you remember the name of the input output ports in the FA? It was A, so you make dot A, parentheses, dot B, dot CN, dot sum, and dot carry out. Then from there, you can connect wire inside the input output ports. So A, it will be connected to ATB. B will be connected to BTB. CN is connected to CNTB. Sum is connected to sum TB. Count is gonna be count TB. Why this is important? Because I can change the order and still it will be working fine. What do you mean, Muhammad, by changing order? I can just actually make it like this. I can take CN and I put it here. And still we'll figure out what is CN in the order. Hey, so you guys understand what I did so far or not?
Professor,
Yes.
why did you make sum underscore TB reg? Why is that declared as reg?
Where?
Right there, top out. Yeah, why are those two?
Because because basically those are the data type. So what happened? You remember in the breadboard, right? You bring the IC, right, from Fry's or from Micro Center or whatever, right? And you put it in the breadboard, right? But then you bring wire from by your hand to connect to the pin, and you connect to the supplier, right? So those are the wires, and the test bench is the breadboard. So you put the IC, and you're hanging out wires out of the input output ports. So this, what is the type of those wires? Are wires. You know, so basically the input in the test bench, we call it wire. So make it wire, wire, wire. The output will make it rig.
Sounds good.
Okay. Now, I have wire hanging from the IC, but I didn't assign anything to this wire to see the output, right? You agree?
Is there a significance to what TB means?
No, no. Here, you know, let me write this. 1 second. A, Mario. B, Khaled. C, Eduardo.
TB just stands for test bench.
You know, Shad. ROHITH.
Actually,
No,
because-
everything is green, blue. You know why? Because, you know, ATB is not exist. I didn't define it, right? So I have to go and add Mario. Mario. Now, Khaled.
Professor,
Yes, sir.
if you wanted to, you could actually flip the wire reg declaration in the test bench if you flip it on the full adder module. That would work as well.
Here it will be wrong. If you flip, it will be wrong. But here, the order is not important. You understand my point? So that's why, you know, the second approach I like more. It's more systematic.
Oh, not the module instantiation. I mean, when you declared the wires within the test bench.
No, you can declare them in any order you want. It's a parallel language.
No, as in the earlier question was, why is it a register and not a wire?
Output in general, I put register.
Yeah, I'm just saying that if you wanted to, you could flip the wires to become registers, and the registers.
No. I will tell you the story, because basically, you know, the output is going in a wave form, right? So that means, you know, kind of a storage happening. So you are storing it, even there is no clock.
Mm-hmm.
It's an organizational thing. So you're storing something to see it. So that's why I make the output rig, even there is no clock. But in the RTL, you have to make it wire. Do you remember? Look at RTL here. I make everything here what? The output wire, right? Because there is no clock. This bench is different because this bench is like, you know, virtual testing environment. Okay? Don't worry, I'm gonna go through it many times and, you know, it will get into it. But it's a completely new language. And also, let me tell you something. Did you see what I did in front of you? I put here the unit and then the wire, right? Let me show you something which is more fun, right? Here. What do you think? What happens?
I suppose it works.
It will happen. You know why? You define, you instantiate something does not exist.
No, right?
Right?
You didn't mention. Yeah.
Yeah, but wait. Let me show you. Wait, we should have something. You know. Why this one it works?
Because they all run at the same time.
It's a parallel language.
Parallel, yeah.
Yes, but the test it's sequential. Okay.
I see.
Okay. Anyway, let's move forward. Now we need an environment which is called procedure block. You will find it later on in the document I shared with you. Procedure block is a block that, you know, will run first just from 0 time and it will never repeat itself. There is another one, it's called always procedure block that will be later, maybe in a week or so I will talk about. Anyway, so this one, I have wires, but I need to push the wire with some values, right? You agree? So we need to know what these values are. So normally the values are binary, hexa, decimal, whatever, right? Documents also showing this, but I'm gonna do it in front of you. So I would say here initial, begin, end. This procedure in front of you is called initial begin. That means, you know, I'm gonna put a value by a certain time. This block will be processed one time. It will not return it back to itself. That means there is no like looping in it. You know what I mean? So you can give name for the block if you have multiple initial, like, you know, block Ali. So this initial block, I call block Ali. Okay. Now I need to push data inside the input, right? Do you agree? So what is the inputs we have? A, Mario, B, Khaled, and C, and Eduardo, right? And what we are expecting to see the output, it will be Chad and Roth. Oh no, can you please tell me your name again, so I will not make a mistake?
Rohit.
Rohat. Okay, so you know, see out Rohat. Thanks a lot. So anyways, you know, so we are basically checking Rohat and, you know, Chad now. So I would say A, Mario, like this, equal, this is what? A single bit, right? It's just a wire, single bit. So I would just say 1B. That means how many bit? 1B binary. And what is the value of this? 0. So what I said, A Mario is 1 single bit, and that bit is 0. Then I say B Khalid, 1B 1. Why is there an error? Ah, okay. Sorry. This guy has to be reg. Yeah. Because I'm pushing them. You're right. Okay. So that's gonna be reg. That's gonna be y. I flipped them. Sorry. Okay.
Oh no, yeah, that was.
Because you cannot push in the wire that value.
No, yeah. That was
Unless you do something. No, wait. There's a way to do it. There's something. It's called force and release. Okay. There is something in this bench is called force and release. So you force value inside the wire. Anyway, thank you, Mario. Then, you know, CN Eduardo. I think I wrote your name wrong, dude. I'd like to be very organized, you know? So I like this. And say here, did you see this sign? So in the test bench, it's giving you initial values. And the value here is normally is by nanosecond. So 10 nanoseconds, what will happen? Maybe we can change the value of Mario, right? But then, you know, I didn't say anything about Khaled and Eduardo. So then, you know, what will happen? The software will keep Eduardo value and Khaled value the same. So gonna be here 1B. Maybe later on, you know, maybe B Khaled will be 1B 0. Then maybe at the time CN Eduardo will be 1B1. No, 0. Then 100 second, leave it as it is. And if you close, you like to close the waveform, so you can do like this. Finish. Okay, now what we did, we wrote a test bench. We instantiate the block we would like to test. We build an environment which is called testing environment around that block using the procedure initial block and the registers and wire as we discussed, and Mario mentioned about the wire and registers. Now, the time to see, yes.
Could you answer the questions in the chat?
There's a question? Where? I cannot see. 1 second. Register store values and will begin to feed those values into the module. Can you explain again why we had to switch red and wire? Yes, sure. So basically, you cannot say that Mario is equal 1 or 0 if you are using wire, because it's a wire. How can you put a value on a wire? But register, you put a value in the register. And, so that means, input should be in the test bench act as a register. Input normally register because you store a little bit data there and then you move forward, you change it. You're welcome. Anyway, so now we need to do what? Run simulation. Okay, look. So you check here in the left side, you will find run simulation. You click and run simulation here. Behavior simulation. Sounds good? I will click. See what will happen. Takes some time, my computer is slow. Let's see what happened. So the waveform we talked about in the presentation, right, is here. Make sense? Look, Mario when is 0, and Khalid is 1, and Eduardo is 1. 1 plus 1 is what? 1 plus 1 is 0, and there is a carry out, it will be 1. Right. And then, if you go here, then Mario is 1, Khalid is 1, and Eduardo is 0. Still, gonna be 1, 1, 1, 1, 1. It's gonna be 1, 1, 1. Then you return it back here. Mario is 1 and Khalid is 0, so 1 plus 1, and Eduardo is 0. So in that case, the carry out will be 1, and the summit will be 1, and the carry out will be 0, which is fulfilling the truth table of the one bit full adder. So what we did, we basically checked all of the corner cases. Now we need to learn how can we do an instantiation in the RTL. So instead of 1 bit full adder, 5 bit full adder, 8 bit full adder. There is a manual way and there is a smart way using the for loop and for GenVar. I'm not gonna give you the GenVar today. I'm gonna do the manual a little bit so can you understand the trick of connecting between blocks. Mario, I believe, or one of you guys was talking about the look ahead adder, but what I'm gonna do, I'm gonna use the rebel carry adder. If you guys remember the rebel carry adder, the carry out of the first bit will be the carry in for the second bit, and the carry out of the second bit will be the carry in for the third bit, and so on. So it's like, threading. So the wave propagation will be significantly increased. Because, do you remember when I made the 1 bit full adder delay in front of you? If you have 32 units of this connected like this, in that case, so the whole entire system, it has to be very slow because it's basically n times 1 bit full adder delay. And 1 bit full adder delay, we calculated in front of you as a 6 nanoseconds if everything had been built with 2 input NAND gates with 1 nanosecond response delay. That makes sense? Or should I make it in front of you? Should I make the 2 bit full adder and show you what I'm talking about?
Yeah, please.
Sure. So now I'm gonna switch back to my tablet. One minute. Can you guys see my screen? Okay, so now officially we have using NAND gates 1 bit, 2 inputs NAND gates response time 1 nanosecond. We're gonna have the 1 bit full adder delay 6 nanoseconds. Do you agree? Now, I would like to build the multiple stage full adder, like 2 bit full adder. When I say 2 bit full adder, I can use RCA which is stand for rebel carry adder. Rebel carry adder. Or I use CLA, which stands for the carry look ahead adder. This is a story and this is the different story. So let's go with this one as a simple version. So rebel carry adder, it means that, you know, I have two things. Each input is our two inputs, 2 bits representation. Do you agree? So in that case, I can just go ahead and do like this. Full adder 1, full adder 2. See, carry in, carry out C2. Sum 0, sum 1, and here is A0, B0, and here is the A1, here is the B1, right? So this is the 2-bit carry, full adder, rebel carry adder. I don't have it. What is it? Does any of the last few lines of the test bench code? I'm gonna show it to you guys. Don't worry. You know, I'm gonna return it back. I'm gonna return it back to the Vivado. We still have time. You know, we have up to 2:15. You know. Anyway, so now we have the two full adders, right? So A0, A1 is A, B0, B1 is B. So A0, A1 is 2-bit, B0, B1 is the B 2-bit, right? Now, what is the delay of this circuit from your point of view? We said one full adder is 6 nanoseconds. Do you agree? 2-bit full adder, what is the delay will be? I can tell you. The second full adder cannot operate until the carry out will happen. All right? So basically, you guys with me? Hello?
Yes.
Okay, so this one, it has to be arrived in order to get output here correct, right? So pretty much I have to spend 6 nanoseconds here until the carry out will come. Then this will take 6 nanoseconds to get output of this, which is opening the door to say an equation saying n bit full adder delay is equal n time 1 bit full adder delay. So in our specific experiment in this one, 2-bit will take 12 nanoseconds. 3-bit will take 3 times 6, 18 nanoseconds. 4-bit will take 4 times 6, 24-bit, 24 nanoseconds, and so on. Did you get my point? To do this circuit using Hadoop description language is not that really hard. Why? We're gonna use the instantiation. We have one full adder. I don't need to build it twice, right? So I'm gonna take this one and repeat it twice in another folder, and I will call it 2-bit full adder. Let's go back to the simulation environment and see how we're gonna do this. Sounds good? Now, simulation. 1 second, please. Oh, somebody wait, somebody need to go back, admit it. Can you see my Vivado?
Yes.
Okay, so now we build the full adder, 1-bit full adder, and I'm tired. I don't want to build it again, right? I'm lazy. So in that case, I'm going to say add design, and from there I say create, and then I will say full adder 2-bit. By the way, you cannot write number in the beginning of the file of Verilog. It will be considered wrong. So have you noticed I wrote first alphabet? So I said FA_2-bit. That's also you will find in the PDF or the PowerPoint slide I shared with you, and I'm gonna go straight with you. Anyway, so here FA_2-bit, and I need to define them. I'm not gonna define it with automatically now. I will define it later automatically, but I just want you to get used to writing by hand. So here I'm gonna say, I'm gonna do it by myself. I'm not a kid. And then I will just go ahead and say, where is my new full adder here? All right, so I will go here and I will say A input, right? So it's input, but this time A is not single bit. A is a bus. So basically I will open here and say is 1 and I call it A. Input also to 1, 0 and B. Then input carry in, it's the same, but you know, to be consistent, CN. Then output will be 1, 0, Scheiße, 1, 0, and I'm gonna be here sum, and then output is gonna be carry on. Then those guys are what? Wire. Those guys. So you see what I have done now? And this is the definition of the 2-bit thing. Now, I need to get the best of the FA. Do you agree? So I can come very easy and say FA unit 1. Then I instantiate again. I say FA unit, let's make it unit like this, 2. From there, I do like this, I do like that. So what I did, I called FA twice, different names. So became 2 different components or modules inside the 2-bit. Now, if you remember very well, the order, I don't care that much about it anymore. So I'm gonna say MA, B, CN, sum, carry, right? You guys are following me? Hello?
Yes.
Yes.
I just want to be sure that everybody is not asleep or something. You know? Perfect. Now we need to fill those gaps, right? So A, look, I'm calling the first bit of A, right? So A 0. Going to be with B 0. And the carry in the first stage is gonna be the coming as a carry in. Do you agree? Sum will be what? It will be sum 0. Carry out now, leave it, okay? Here, it's gonna be what? A1. Here, B1. Here, carry in, leave it also. Sum is gonna be sum 1. Carry out is carry out. Do you agree? Now, if you remember from the tablet, right? There was a wire coming from this going into the second one, right? So that means I can literally define a wire here in the middle if I want, and I say wire. No, I can just put you wire temporary carry out. And I take this one as an output of the first stage to be input of the carry in of the second stage. So what I did in front of you, I built the 2-bit full adders using the instantiations which Verilog give it to us in the synthesis environment. Now, do you know whether this thing is working correct or not? You don't, but I want to show you something. Look into the design source. Have you noticed something? Somebody tell me what you noticed. You guys can speak, go ahead.
It's showing the 2 instantiations.
Exactly. So that means show that this thing have been connected by 2 ICs. There is 2 ICs. One is called unit 1, unit 2. Each one is full adder. That makes sense? Now we need a test bench. So we create a new test bench. And this test bench, I will call it what? Full adder 2-bit TB. You guys remember there is no in and output ports, right? So I can literally take this copy now and go into the new test bench. This one. And we have a steps, right? Somebody will ask me why you did that. I would say because, you know, I don't remember how they look like. So I just put it like this, FA 2-bit and I'll go like this, A, B, C, N, some carry out. Right? Now I don't need this anymore. Did you see what I did? Just to remember the name. If you remember, like Mario said, 120 ATB semicolon. Close with semicolon. Then reg 120 B TB, and I say TB because of that test bench. Okay. Now reg CNTB. Now wire 10 some TB wire carry out TB and I put them here, A TB B TB CN TB some TB C out TB. What is the next step from your point of view? We will start to insert what? Push input into the module, right? Initial, begin, and Muhammad. Move. Now, A TB, it has a value. You can make it like this. That's called blocking, non-blocking. I'm gonna tell you about it later. B TB, it has a value. C and TB, it has a value. And let's see how we can make the value. So you remember I told you that, you know, last time it was single bit, right? Now we can make it, it's a 2-bit. So you can write 2B and a value, like 10, for instance. You can also write it 2D and you put a value between 0 to 3, because 2-bit will bring you 0 to 3, right? So you can say 3. right? You can write it 2H hexadecimal, and you can put a 1. So you can make it with any multiple way. You can just write, 2. You know what I mean? So here's 2 and binary, and they're 2 bits. There they are 2 bits, I agree, and they're decimal, still decimal, and I will put value between 2 bits. That means 0, 1, 2, 3. Let's say 2. Then carry in, it's basically 1 binary, right? So basically 1 be 0 or 1. Let's say 0, right? Or 1, I don't know, 1, right? And then you go ahead and say delay for 10 nanoseconds. Then you take a copy of those, maybe you change the values, it's up to you. Let's say that 3, 1. Oh, you cannot do this because it's a binary. Let's say D. Let's say binary 0, 1. And let's say 1. And then, let's make it like that. And then you say here. You make it 100 nanoseconds. Okay. Then, if I run the simulation, let's see what will happen. Simulation here, values there, and here's the value of Mario. Oh, did you notice simulation didn't work? You know why? Because we did a mistake. And this is very important to know. Let's see. Look at the simulation. Did you see this little, like a triangle sin with green in the left side? It's in the stop on the FATB, which is actually testing 1 bit full adder. But there is another test bench we wrote here, which is called F2-bit TB. You have to set it as a top. So you click right here and sit as a top. Or you can click on this and say, simulation is setting. And from there, you can pick up which test bench you need. This one is much easier, right? So I would just go and say run simulation on behavior. There is an error. I love error. Should have an instance name. We forgot the name. Oh yeah, we have to make an instance name. Test bench T1. Then if you make a simulation, it will pass. But do you see how I actually debug the code? I'm teaching you the practical way, which is most important. After that, theoretical thing is really easy. So look, 3 have been added to 2. So that means 5, right? And then, and then the carry in is 1. So 2 plus 2 is what? Huh? Hello? Hello? 2 plus, can you hear me, guys?
2 is 5?
Yeah, 2 plus 2 is 4 plus 1 is 5, but 5 more than what? 2 bits. So the output will be 1. Right? Do you understand what I said?
Yeah.
Okay. So 2 plus 2 is 4 plus 1 is 5. So there is carry out actually, and it will be 1 because there is extra bit went out. That's actually why people use the overflow, right? Then 3 plus 1 is 4 plus 1, 5, the same thing. So this test bench didn't actually cover the corner cases. Do you agree? So how can we cover the corner cases? We put all the possibilities. So the possibility it can be, make it 0, 0. And then, 0 plus 2 is what? 2 plus 1 is gonna be 3. So at least you can see number, right? So I say run again. It would say, can you please change? Change. How is it going? 2 plus 0, 2 plus 1, output 3, and I don't have a carry out. But when I went more than the 2 bits representation, carry out went out. So the test bench is correct. So far, so good, guys.
Yeah.
Did you guys learn anything useful today?
It was all these.
Yes.
You learned a lot, right?
Yeah, use and practice.
Yes. What is the best way to do? Practice. Practice. Don't worry about the book now. Worry about, to be feeling the test bench, to be feeling how to build the circuit. Next time, we're going to talk more about, Monday, we're going to talk more about, behavior modeling, data flow modeling, building different circuits. And then I will give you also a task for Wednesday. You guys will work on it. And then every single group will come to me in a specific slot of the time during Wednesday to present their work and show me what do you learn so far. And then, I will give the grade based on this and we'll move forward. Do you have any question? Eduardo, do you have a question?
No, no question. Sorry.
Okay. Mario, do you have any question?
It's kind of an off-topic question, but what app do you use to write on your PowerPoints?
What app I use in my PowerPoint?
Yeah, I saw you were able to write on top of your PowerPoints. What app was that?
Notability.
Notability?
Yes. Do you have iPad or what?
Yeah, and I was kind of looking for a program like that to write on
It's
top
amazing, right?
of. Notability.
For
Okay.
Notability. I think I spent like a $10 and just one shot. They don't take money from me yearly, just like one shot.
I see. Thank you.
Do you guys have any other questions? Do you want me to write it down to you? It's called Notability. Let me see.
Professor, so we'll be given the homework on Monday or like through Blackboard?
What do you mean by homework?
Assignment.
Do you need assignment?
Didn't you say there was going to be an assignment due Wednesday?
Yes. Did you get the board? You haven't get the board yet, right?
No, not yet. Probably going to arrive later than Wednesday for me.
So that's why, I'm trying to be a little bit slow in this until everybody will get the board. But I will assign something for Wednesday for sure.
Okay.
But after I give Monday. Okay. What else? So you know exactly where you're gonna find the material, right? In the Blackboard. I just need to be sure everybody in align with me, right? So CBB. Yes. Back to the thing. I'm sharing the screen with you. Can you see it? Can you see my Blackboard?
Yes.
Yes.
So Blackboard, we are 3300, right? Here, course documents, week 1, recorded lecture. You can find my old lecture, right? The Monday one.
You're going to put everything in the lecture tab. Nothing's going to be in the lab tab, right?
Yeah, I mean, lab and lecture same.
Okay.
I can put the identical thing there. There's no problem. Okay. Then, from there, you open the supporting material. You will find the material I shared with you today. You will open the recorded lecture. You'll find the old lecture plus the new lecture that, I'm recording at the moment for you. Okay, look. Do you guys in favor also to, so I can make a copy of this also there in the lab?
You cut out for a second. Could you say that again?
So, Khalid was asking, should, he will not find this type stuff under the lab. So I said, I'm asking, you guys like me to copy this also under the lab as well? In the Blackboard?
Lecture is enough.
Huh?
Just put it in the lecture tab is enough. You don't have to do it twice.
That's what I did. But, in general, I can also make a copy here in front of you and say that, I would like to copy it in the, no, not here. I will just say here, I want it in the lab, right? Here's the lab.
Is there any one that's just in your lab and not your lecture?
I will put it in both. Submit. So now if I go back in the Blackboard, you open the 3300 here, you open the course document, you find everything there, copy it. Okay? So you will find them in both 3300 and 3300 lab. Sounds good?
Sounds good.
Super. So thanks so much for your time and for attending the class. And, I really appreciate it. And I hope that you guys are enjoying the course. So thanks so much. God bless you. Stay safe and talk to you on Monday. Thank you.
Okay, Professor. Thank you.
Yeah.
Professor.
Thank you. Bye.
Have a good day, Professor.
You too. Thank you. Bye-bye.
Thank you.
Thank you. Thank you, Professor.
Thank you. Bye-bye.